When I started these videos about relativity, Doppler effect, relativistic time, all this kind of stuff, I was really trying to justify this goofy equation that is supposed to change the universe, E equals mc squared. So finally, after all of this stuff, I'm going to try to get to this and just show you what the assumptions were when we came up with this value, because assumptions are just right. Don't ever trust that science is absolute truth. It's just somebody's best guess, and math does help us come up with these best guesses. So here we go. More math. I don't know any other way to do it but to include some math. So E equals mc squared. Hang on to your seats. Here we go. All right, hopefully you're ready for this. I'm going to go ahead anyway, even if you're not. Uh, the term work in physics is considered force times distance. So think of it this way: you have an object that you're applying a force to, and you move that object a certain distance. That defines the work. Okay, force times distance is work. Now, what do we need work for? I thought we were going to talk about energy. Well, we are going to talk about energy. We're going to talk about the fact that the change in energy equals the work that's been performed. And whether you buy that or not, let's just go ahead and live with it. And the change in energy, if we talk about what I just put up here, force and distance, there's force times delta x. The delta means change. All right, are we done? Well, there's the E, so we're getting close to E equals mc squared, but not there yet. Here's force. Now, what you probably relate to is force equals mass times acceleration, Newton's second law. Well, that's not exactly what Newton had in mind. Actually, Newton had change in momentum over time. Change in momentum. That was his big deal because mass was really defined by momentum. If you have momentum, then you can define mass. You don't actually put it on a scale or anything, you define it with momentum. And momentum, which we had from this last one where we figured out the relativistic mass, momentum is equal to mass times velocity. So, does that make sense? I can't hear what you're saying because this is a one-way video, but I'll just keep going. Okay, now let me put it in this form. Rather than delta P, I'm going to put this little d here and a little d down here. Now, what's the difference between the delta and this little d? Well, these are called differentials. And what they mean is they're infinitesimally small so that we can get down to really fine. Anyway, it's going to be necessary. Forget why, but just go ahead and live with it, please. So I'm going to take the differential or the derivative of mass times velocity, which is what Newton said, and I'm going to do it in a little different way. I'm going to say that velocity times the change in mass with respect to time. Now, that's a big deal right there. Change in mass. How can that be? How can that be? Let me put a little indicator up there that shows something's really weird so that we remember that. This should cause a problem for you. says the change in mass over time. How can that be? Does mass change with respect to time? Our normal thought is mass, it's not changing. So the change in mass with respect to time is just zero. And the result we get is mass times change in velocity with respect to time, which is the same as acceleration. So that's what we should be comfortable with. But what we learned in some of those other videos about relativistic mass is the mass can change. If you get really close to the speed of light, then the mass starts showing up as something different. So, with that said, let me go back to this where you can see my cursor a little bit better. Now I'm going to come down here and take all this garbage, which is force, this force here, and plug it in right there. So this is just a copy of what I had over there. And then I'm going to put, instead of delta x, I'm going to put the little dx, which is the differential of x. Now, here's the method to my madness is I'm going to multiply dx across these two expressions. There's dx, dx, dx. And then I'm going to come down here and juggle things around. I'm going to put the dt under the dx in both cases, and I'm going to have the velocity times the differential in mass times dx over dt. Well, guess what? Dx over dt is velocity. Change in distance with respect to time, that is velocity. So I'm going to be able to double up my velocities here. Okay, let's take this fact that v equals dx over t and see what we can do with that. I'm going to take the dE, and notice what I'm going to do is the dx over dt is v times dm times v, or v squared dm, and then come over here, and dv times dx over t is really mv dv. Now, somehow I've got to prove that v dv, this quantity over here, is equal to 1/2 dv squared. How am I going to do that? Well, let's take this, work it backwards. What we want to do is get a differential of v squared so that we have this pattern v squared dm plus m dv squared. So dv squared equals, now let's think of it this way. One of the v's, I'll just take v1 times dv2 plus v2 plus dv1, and really, since the v's are the same, this is really the same as 2v dv. But to get rid of this 2 or cancel it out so we're making a good substitution, it comes out to this. Change in energy equals v squared dm plus m times 1/2 dv squared. Why did we do this? The next step will be to figure out why I came up with this thing. So we're going to start with this on the next section of this. This is a mess. This is a total mess. But look what I end up down here. E equals mc squared. What does that mean? Well, let's just go through it. Here's the two things we had. Change in energy equals v squared dm plus 1/2 m dv squared. That's what we just dealt with. And v squared equals c squared times 1 minus rest mass squared over relativistic mass squared. I think I proved that somewhere. Hopefully I did. Anyway, what I'm going to do is plug in this v squared where these v squareds show up, which is what helped us out on this last one. So the v squared, instead of v squared, it's c squared times the quantity 1 minus mo squared over m squared dm. And dv squared is little d out in front of c squared minus c squared m0 squared over m squared. M0 rest mass, m is relativistic mass. Isn't math fun? Anyway, let's keep going here. Now you notice I went ahead and multiplied the c squared through. There's method to my madness there. Anyway, change in energy is this. Notice there's no change in this term. Term is where you got things multiplied together. And this term, what do we get? Instead of c squared, I put a 0. C is a constant, so the change in a constant, zilch, nothing, 0. This one, however, I take the constant part out, c squared rest mass squared, and I have d times m to the, what happened to the m squared in the denominator? Well, I just put it as m minus 2. There's a reason why I did that. Definite reason. That reason will be seen in this next step because I took the 0 out. That doesn't account for anything. And, oh, wait a minute. The minus had something to do, so I put the minus out here in front of the 1/2 m. Then I did some magic, which those of you that have had calculus and know about how you take derivatives, you take the exponent. This is the magic rule of the derivative, is that you take this exponent minus 2 and then you subtract 1 from this exponent. So that's why I put it in the minus 2. So there's a minus 2 out front and m minus 3 dm. It is getting really out the window, isn't it? Anyway, let's come down here. Now it's getting fun because things are getting, look, this one's a lot shorter. So I must have had some luck here. Here's the c squared. There's a c squared in each of these sides. So I pulled the c squared out. And I notice there's, notice I have m squared. Well, how did that happen? Well, I've got m here and m cubed in the denominator. So one of those m's canceled out, and lo and behold, we've got an m squared down there. So I've got an m0 squared over m squared, m0 squared over m squared. Got a minus 1 here, a plus 1 there. And isn't that nice? Something disappears here. This just becomes 1. So all that's left is c squared dm. Now we've got something. Now we can work on something here. Let's see what we can do. This is major event here. It's not E equals mc squared, but darn, doesn't that look close to it? The change in energy is 0 if the change in mass is 0. Okay, change in energy it's not gonna change if the mass doesn't change. Well, in our normal world, you say the mass of a 1 kilogram weight, it's going to stay a 1 kilogram weight forever. But in a previous video, we talked about relativistic mass, and the mass can change. And when the mass does change, then we have a change in energy. And that energy can be rather large. As you can see, speed of light squared, super big number. So if we got some change in mass, that's going to be a big difference. So what I'm going to do is, using the good form of calculus, I'm going to say if I integrate this thing, then I've got to come up with a energy and a constant. And the constant was that we had zero energy until we had the relativistic mass. And here is E sub k, which is kinetic energy. The mass won't change unless we're moving, right? If we're moving, then the mass changes. Look at how many assumptions are being made here. But anyway, this is where all this stuff comes from. And that's the point of this video is E equals mc squared. Who thought of that, and how did it come about, and how do they justify it? Also here, I've got on this side c squared equals m minus m0. Here's the relativistic mass minus the rest mass. The rest mass is if we're not moving. So here we go. Here's our final step. I hope you survived this trip. If not, then apologies.